Okay, I'm going to go ahead and get started here. I apologize for the beginning of this class because this is probably one of the more boring topics of this course. And it should be one that you see before. And that's discussing interrupts. I have the slides that I use for it, but I can't find them, so I'm just going to talk off the top of my head and use the book as a reference. I'll probably go to one that kind of shows you things. First off, let me just kind of jump through here. This is coming from the one book that you should be, the 8051 book. But let me just kind of go through here and just kind of point out the highlights here. An interrupt is an event or occurrence. Something happens that we want our microprocessor or microcontroller to do something. So an interrupt is just something happens and we want to service. We want to take care of it. The easiest example I have for that is, and I pick on nurses all the time, that they're, because this is a good example. Think of a nurse working in a hospital, not Dr. Hall, but in a hospital. And they have a little nurses stand where everybody sits in the kitchen, drinks their coffee or tea, or everybody drinks tea, and read books, and do various things. So, at the nurses station, there's a panel of lines in many hospitals that are wired to the various patients' rooms. So if a patient pushes a button, they're asking for the nurse to come to the room to give them attention. Same thing on an airplane. How many people fly? Been on an airplane. None of you been on an airplane. I think you said exactly. But on an airplane, there's a little button where you can push to call the flight attendant. Tell them that you want to go over, you want to eat, whatever, you want a blanket. These are types of things that cause interrupts. These are interrupts. If you have a house with a home security system, the front door opens, it sounds an alarm. That's an interrupt. It's any type of event. We're right both like microcontrollers, all kinds of things can happen. An interrupt might be something, say, a gasoline pump, the pull indicator trips. The car is filled with gasoline, so therefore it triggers an interrupt. You want to do something right there. So interrupts are lines, and we have multiple interrupts in the 8051. Multiple interrupts, many interrupts. The original 8051 had only 6. The one that got the blower motors going on there. So what we're looking at, when we look at the 8051, and I can't find my slides for this, so I'm not going to read all this here for you, but what happens with an interrupt is that there, and this is getting into the technical aspects of it. I'm going to sit down here. And what is this thing telling me here? Oh, let me close this right here. That's my previous class is done. Right there. Okay. All right. This is what I'm trying to get to is this table here. On the left side of this table, this is our interrupt table right there. And this is on page 250 of the one book that deals with the Silicon Labs there. It's called Embedded Programming Textbook. Right there. I think I posted it online. Everyone should have a copy of that there. Right there. All right. As we look at our interrupt, we've got 4 things on this table here. One is our interrupt source. This is what causes our interrupt. And as the number one highest priority interrupt, most important interrupt is the reset panel on our microprocessor. When that is tripped, it is always enabled, it will do what it's supposed to do. When that happens, the microprocessor automatically goes to address 0000 and starts executing code. Right there. The microprocessor is running along, and all of a sudden, an external interrupt on pin INT0, I'm using Intel calls IPR, but IPN0, that line goes low, that triggers an interrupt on the external interrupt. That's on pin, it's on the pin, you set up to the crossbar if you want to use that interrupt, and it's priority 0. That's highest, second highest here. And it's going to go to address 0003. You can start executing code. Now, all the interrupts other than the reset have to be enabled. If we want to use interrupts, we have to enable the interrupts. So, we can pick and choose what interrupt we want to use. Right, that's where we have to use any interrupt but reset button. Right? That's the only one that we've used. Now we've got some registers, and I'm not going to dwell on this. I'm just more concerned that you understand what interrupt is and how and what we do with it. But as we look at this right here, these are our interrupt priority numbers. So it's the second half of today's lecture. I'm going to do, for example, a timer 3 interrupt. This interrupt higher port priority right there. So we've got right there. So the interrupt process, and this is really the key thing that I'm wanting to get across here. Is this process right here, is that the microprocessor completes what it's doing. So in other words, it's executing code. It's going to finish the current instruction. It's not going to stop mid-instruction. Just like if you're reading a book, most people won't stop mid-sentence. They'll finish the sentence they're reading. That's it. So if you're cooking and you're putting oil into the pan and the front doorbell rings, you go ahead and finish putting the oil in the pan, turn off the stove, and go answer the door. Again, that's another example of an interrupt, a doorbell. So you don't sit there and look at the front door, watch people, look for people to come. You go and do everything else in the house, and when the doorbell rings, you go and answer it. Simply from your telephone. These are all interrupts in normal, their everyday life, right there. So we complete the there. Then we got to save where we're going. That's where I like the nurses. That if a nurse is reading a book, and this actually probably works better in the U.S. because nurses are notorious for reading trashy romance novels while it's working. They put a bookmark in the book so that they know where to go back to when they put the book up. So that's what the CPU has to do. It has to remember where it was at. Everybody in this class is under the age of 20, 22, something like that. You don't have to write notes for yourself to remember what you were doing last, right? You get over 60, I'm not there yet, but my wife is. She leaves little notes for herself all the time. The things that she remembers where she's at on doing a particular project. But if we restore, we have to keep track of where we're going to. The way the microprocessor does that, it has something called the stack. The stack is, and you shouldn't worry about the stack in every microprocessor. It pushes the address onto the stack. And you should have covered the interrupts in your first processor class. I just want to kind of touch on this a little bit. Because the next topic I'm going to go to is C. So we push that there. And then we load the program counter with the address of the vectoring of that table. So if it's the INT 0 interrupt, 0003 is popped into the program counter, and we start executing code with that address. Now, one of the things I should point out is this interrupt vector table only gives us like 3 bytes for the reset and like 8 bytes for everything else. I mean, we don't have a lot of room in that the interrupt vector table, IVT, interrupt vector table, to actually execute code. What I've always suggested, if you write in assembly language code, you just simply put a long jump to where you write the code. Right there. So we'll see here in a minute how we handle such an interruption. It's fairly easy, and it's even easier in C. But this is what happens. The last command of every interrupt vector or interrupt service routine. We're two different things. Interrupt vector table is the table that contains all the addresses of all the various interrupts that can occur. The interrupt service routine is the actual code that services that. The doorbell rings, you have a process you go through. You're going to service that interrupt. Normally it's you walk over the door, you open a little bit and see who's there, and then you open the door and say, that's my code, come on in, or whatever. But you way of handling it. Some people have cameras where they'll turn on the camera to see who it is and talk to the speaker. But you have a process you go through to handle what you do with the door over. Say they do the phone rings. You service that interrupt. You don't think of it as an interrupt service routine, but when your cell phone rings in your pocket, what do? You pick it up, you look to see who's calling, you move the button and answer, right? You process it. We have to do the same thing with processing. Is that when an interrupt occurs, we have to service it. And we do that with an interrupt service routine. We write that. That's a code that we're writing. That's there. And I should point out that probably next week, I think I'll talk about that later. Not there. So once we service the routine, then the last code in our interrupt service routine is going to be a return from interrupt command, RETI. And we have a normal subroutine that ends with a return, right? But we want to tell the processor that we want to do an return from interrupt because it saves a few extra things that I'm not going to go into detail on that there. But it does push the return address, but it also saves the status, program status words and all that, because with a normal call command where you call a subroutine, we don't worry about those there. But when we're doing an interrupt, we don't know what the next command is. It may be a jump if no carry, it may be a branch of 0, jump branch of not 0. It may be some type of jump command that looks at this program status word. So it has to be stored. So all that stuff has to be stored. Right there. So again, we'll continue executing where it left off. Some interrupt are automatically cleared. There's some other things happening. I don't want to get into detail. This is you can spend hours digging into this, and it's really not critical. What you really have to understand is the process that occurs with the interrupt. And how you use that, because the next couple of topics we're going to be looking at, we're going to be using interrupts. That's why I'm jumping into that there. Our interrupt vectors, right here. This is an example of how we will write code to use an interrupt right there. So we're going to use, in this particular case, timer 4. Timer 4 is located in the interrupt vector table. This is where you have to have this table in order to write this code. There is you would look at org 083. Now in C, you don't have to worry about that. We're going to talk about C toward the hour here. But when we look at this table here, in assembly language, you have to refer back to the table. In this table here, timer 4, right here. Why is my mouse doing its thing? My computer is doing something funky here. All right, well, I'll put it right here at the top of the screen. Right there is 83. You see the 83 there where it says timer 4 overflow. So when we look at this right here, we put the org 83x. That's the address and the interrupt. Someone throw some cold water on her friend up front here and that there. There. Actually, that's not the first time it's happened to me. Normally it happens at 8 o'clock classes. There. 10 o'clock classes, usually people are awake by then. Okay, getting back to our discussion here. All right, C segment 0, long jump main. Now remember, interrupt, the reset is a interrupt 2, right? And it's located at 0, 0, 0, 0. So we set in our code segment at 0, our first command is a long jump main. Oh, man, allergies. Now, we've got our next interrupt right there is org 83. So when we do our org 83, that means that we're going to stick the next line of code at memory location 83 in our code segment, in our code memory right there.
And our command we want there is long jump to timer 4 interrupt. Now you can call that whatever you want. That there, you can call it whatever you want. Okay. And then down here we have our main routine that does whatever it's doing. And it does whatever it's doing. This is our code. It can do whatever. And it's going to execute forever until timer 4 overflows. When timer 4 overflows, it's going to jump down here to this timer 4 interrupt function. It's going to execute that function. It's going to see the return from interrupt and go back to where it was at. That's all. That's what's going to happen right there. We have some external interrupts. Now, if you're going to use the external interrupts, that is a little bit more complicated, and I'm not going to go through it with this class in great detail or at all, really, other than to point out if you're going to use external interrupts, right there, I bet you I've got AAA batteries. I bet you my batteries are going dead. They're about 3 months old. Okay, all right. External interrupts, you have to set them up through the crossbar. So you've got to go through that crossbar setup. I really have not gone through that in great detail with this class. One semester and there, your first introduction. So, but if you use the external interrupts, they have to be set up, especially for our processor because it's only got 18 pins, right? 2 of the pins are VCC and ground, but we've got 16 pins. Those 16 pins can be whatever we want them to be, depending on how we set up the crossbar. And by the way, there's a little hint there. You need to know what the job of the crossbar is before you take the final exam. That's a hint right there. So you need to know what the purpose of the crossbar is. You don't need to go on set up. But you have to tell the system that the microprocessor that you want a particular pin to use as an interrupt. Right there. So when you do that, and I went through the crossbar already. I know that. That there, you would tell it that you want to use those particular pins as external interrupts. That there. So there's two of them that they're normally edge strict sensitive, but they can be set up as level sensitive. But those are external pins that we use. Typically, if we're doing some type of control system, we will be using external interrupts for various things. So you would set those up. Unfortunately, we don't have a lot. We're not doing enough labs in order to get that done here. So, but those are the external interrupts. Kind of, there's some latency. I don't want to dwell on this. The latency just simply means the time the interrupt occurs to the time it's actually processed can be up to about 18 clock cycles, system clock cycles. But if you think about it, if you run a 2 megahertz clock, 1 clock cycle is what, half of a microsecond roughly. So 18 clock cycles is somewhere right around about 9 microseconds. Right there. Not a lot of time, right there. So for 90% of what 99.9% of what we use in 8051 for, this latency is something we can ignore. All this latency is because we finished the current instruction that we're on before we respond, is what they're talking about by latency. It's a time delay from the time the interrupt occurs to the time it's processed. Okay. And it could be up to, as I said, 18 clock cycles. That's system clock cycles. Right? So that's all that there. All right. Interrupts, special function registers. Everything's handled in the special function register. Our first one is the only one that exists, not the only one, but it's the one that exists in the original 8051. And this is the one that we look at the various bits. We've got bit 7 enables all interrupts. Bit 0 disables all. Now, when this command is set, EA is set to 1, that simply means we're enabling the interrupts. But we have to enable them each individually what we want to use. Right there. So as we look at this right here, right there, Bit 6 is not used, really. If you look at the original 8051 code, it's just not used. Silicon Labs is set as a general purpose flag that you can use it for other purposes. It's not really part of the interrupt processor. 6, interrupt 2 enable, UART enable, timer 1 interrupt, external interrupt 1 and 0, and enable external interrupt 0 right there. So this just simply, and again, you wouldn't memorize this table. If you did a lot of programming with interrupts with this processor, you would probably learn that. But keep in mind that you would just simply, you would just simply set bit ET1. You wouldn't have to remember that that's 3 right there. But when you want to set the interrupts, you have to set those there. That there. You can play around with the priorities. I'm not going to talk about that, but you can adjust the priorities differently from that table that was given before. That there. And then there's the extended interrupts. These are the ones that were not in the original 8051. Again, very boring topic. Very boring topic. That there. And I'm not, as you see, I'm flying through these here because they're really not that critical right there. This just simply says that we've got some, these are some flags just simply saying that we've got some external interrupts pending right there. And again, I'm not worried going to spend any time on that there. These are the port 3 interrupt flags. We don't have port 3. So that's really everything I'm going to talk about interrupts. That's a fairly short discussion out there. Now what I want to do is kind of bounce back here to, and I'm going to use the same book since I can't find my slides right here. Right there. And I need to go buy some batteries. Right here. No. I want to, before the ADC. Okay. I want to talk a little bit as soon as I find it where I'm going here. I'm just going to use this book as it's kind of a talking point. I'm jumping back to chapter 6. This particular ebook doesn't have any. Okay. All right. Almost to the beginning here. Okay. Okay. Assembly language is not the language that I normally use in gaming. I know we spent the last 10 weeks using an assembly language. I almost never use it for real projects. There's a reason I don't use it for real projects. It sucks to use it. It really does. The code is long, it's run out, it's hard to read. 90%, or I'd say 95% of microcontroller projects are written in C. So C is language. I know everyone's taking a course in C, right? You take a course in C. Because I'm teaching the second half there right now because the instructor is going off to finish for PhD, so I'm teaching the math part of this class. So I know that there's a class. I don't want that to taught us. The amount of C that I'm going to cover today is probably tiny. It's just what we need to go through because our next discussion is going to finite state machines, which is my favorite way of designing microprocessor, microcontroller code for control applications. Has anybody ever heard the term finite state machine? You've heard the term? Probably haven't spent much time on it, right? Well, we're going to spend a fair amount of time on that. Okay, but C is the language that we use. Now, the version of C that comes with the software that we're using from Silicon Labs is the El Cheapo freebie version. We didn't pay for it. You know, I just went to the website, I downloaded it, I bought the boards, I made sure they worked with it. I'm happy. It's the cheap version. We're limited to like 4K of program size, Another code we're writing on this campus is going to be more than 14 code size. It's a pretty big program. So it's picking up, but it does have one major drawback in that it's an integer only file. It does not handle floating point numbers. Right. So functions like cosine, tangent, all those things that exist in real C don't exist in this compiler. They do exist if you want to spend roughly $3,000 US to buy the full version, which is somewhere with the current exchange rate right around 11,000 rates. All right. So obviously, and I think you want to see. Obviously, we've got 20 seats in that room roughly. For me to put that compiler in there, we're talking the 20 times 10,000. We're talking, 110, 120,000 RL just to buy the seat compiler. It's not money well spent. So we're gonna get by with the El Chico freebie version right there. So just to kind of point that out there, if you require floating point full license for the Kyle C compiler, it does exist. In the U.S., I have a full version of that we did use for some student projects that we bought at a university discount that I found we can get here. It only costs us about 1,000 RL. We had one copy. And when students wanted to use them, they had to come up and down, check out the software. They would install it on the machine, and then they would have to uninstall it, clear the license, and bring it back. And I would check to make sure they cleared the license. Otherwise, they're paying for another copy of the software. So it's quite expensive right there. So the first thing we want to do here is when we use C, we always put this include. We did the same thing in assembly language. We want to include this, and in our case, it's not 8051F020, it's C8051F850.H right there. So we just include that. And all that file does is it tells that all those port locations that there, and it gives them the name so that we can do things such as P1 equals right there. So it's a very, very easy thing to look at right here. Basic C structure, and we'll go through a couple of demos right here. This is a typical where you would, this is the simplest program. As you look at this, what does it do? Absolutely nothing, right? All it does is disable the watchdog timer and just sits there and says, while 1 is still equal to 1, just keep waiting for something to happen. So, but this is a very simple program that all it does is right there. But this is our basic shell that we have to work with. In reality, what you would do is you would take that semicolon, you would put your code under that there. We put an open bracket, you would stick the code. And I'll show you an existing one. I didn't bring the board with me, but we'll put it right there. So we're not going to worry so much about the program model. We could say fragment small. I never bother with that. The compiler will actually look at the code instead of the programming model we want. All the code is doing small. But we declare our variables just as we did before. They're connected. It doesn't really matter too much. Keep in mind that we are dealing with C, and so in this particular case, X and Y are capitalized, so C is case sensitive. So, and we have all of our standard types available for us. Int and char are the most common what we'll be using. Now, char, I should also point out, is an 8-bit number as well. We can find something as char and refer to it and treat it as a number. Char just simply means that it's 8 bits. Int means 16 bits. Right there. We got plenty of memory right there. There are stored persons. Okay. Right there, integer variable are stored in the next external memory. Now you can also put in here X data. Everyone see where it says int data X right there, and char data initial, and then char X data Y, and the chart, X data, that there, you can choose just to say it and not palette or stores. As you recall, this particular processor uses external RAM and internal RAM. They're both on the same processor. We only got 128 bytes of internal RAM, and we've got several K of external RAM on this processor. So in most cases, you're going to go ahead and just find most of your variables in the external. So you say X data. So that's an important difference between that and normal C. And what C compiler did you use? The standard Microsoft, what do they call that? Studio, Visual Studio? Yeah. See, none of this stuff would apply to Visual Studio. So, but again, you have to keep in mind that we're dealing with a microcontroller. We're not dealing with a i3 processor or AMD 8086 5th generation, 6th generation processor. I think we're about 8th generation. We're dealing with a microcontroller with very limited memory, so we have to be a little bit aware of where it's putting things. The default is internal, right there, where the default memory, with the use of the program extensions up there. I usually just leave the have and just putting X data in front of anything of any size, right there. It doesn't really. What? Well, you got to remember that this particular processor has the original 8051. This goes back to lecture number 2 or 3. The original 8051 only has 120 bytes of RAM. The Silicon Labs processor we use has that 128 bytes, but inside the chip, it has another 2K to 4K or 8K, depending on which model that the compiler treats as external, but in reality, it's internal to the chip. So, and as I recall, I pointed out that it's very confusing. It's very confusing because we call it external, but it's on the same chip. But it goes way back to that model that we showed early on, where they talk about there's internal memory and then there's external memory, but still on the same device. Just like the analog and digital converters that are on this chip, they're not part of the original 8051. So this chip is a little different. So this creates some confusion. So you can say external, but that doesn't mean there's external memory. It's still on the same chip. Right here. So, right there. We can set up, constants, char, code is equal to character return. That's just like C, that you had there. We probably didn't use very many constants when got there, but they do come in handy. Now, one of the things that are different right here is that we do have something called a bit data that you did not use. In other words, a bit is that. It's a single bit. A 1 or a 0 or a flag. Actually, the closest thing you would have had to that in C, did you guys cover Boolean variables, which are true or false? Boolean variables are bit variables. Right. So it follows that same type of thing. That's bit is declare variables in process for bit field. So we'll look at some of this is all fairly boring until you start seeing some of the codes right here. Now, right there. Now, keep in mind that the special function registers are all defined for us already. So you've got P0 is already set to 80, P1 is already set to 90, and that's just like we did in assembly, right there. Our timer 3 is already set up, where we're going to SFR, right there. Now we can actually specify if we want. I have not done this. We can actually specify variables and give them an exact memory location in memory. That's something that you would never do with a Microsoft compiler. So we can say that we want X stored at location 40, right there. Right there. We can specify that. I have not used that for anything. Right there. That would be used more if you had memory mapped. Well, you could do that, but see, all the ports are already mapped out there, so I can't think of any reason I would use that there. The rest of this is the standard not equal to, less than, equal to. This is standard C. You should remember that there. The logical and, the logical or, the logical not, those you should have seen. Now remember that we will probably be doing more bit operations here than you would do with normal C, because we want to set and clear bits right there. So we want to invert, say, a particular register, or we want to do an XOR on there. So we've got these bit-wide logical operators that they're, you would almost never set a particular bit that they're not. Now, so this is an example that if we want, what did I do here? Is that if we want to set at memory location 21 a particular bit, we OR it with 04 right there. And what that does is it sets, here's our 04 right here, right there, you see 04 here, right there, and it just sets that bit there is all that does. We use the OR. And we do the same thing with the AND to clear a bit. We want to clear a bit, we would AND that. And the reason this is important is because we want to turn on or off particular bits on a port like our LED. Again, that's something you would not do with a Visual Studio, is that you're not talking hardware. Here we're talking hardware, and things, motors and lights and LEDs and sensors and things like that are tied to pins on the various ports, and we want to access those pins directly. Now it turns out there's an easier way of doing that, right there. See, this is all standard C, right there. Again, this is, enabling the crossbar is enable the crossbar with weak pull-ups globally. You just set that up. That's what we did before. And see, enable port 1.6, which is an LED, as a push-pull output. So all we're doing is we're setting that bit right there to a 1, and we're using the OR equal function to do that. Right there. This command there, the line is bitwide OR, and C allows the use of shortcut. That's the same thing as saying P1 mod out equals P1 mod out or 0x40 right there. It just saves the typing. It took me a long time when I first learned C to use that, because I thought it was too cryptic, but the more I use it, the more I got used to it. So we have the same thing. We have if then else commands available to us right there. If 10 is greater than this is standard C. It's with minus the floating point with the addition of the bitwide operations right there. We can do if then else's right there. We have all those options right there. The switch command we're going to be talking about in much more detail here later on. Probably maybe tomorrow or probably next week, when we get into actually coding finite state machines. The switch command actually is the ideal tool for that. Right there. Tomorrow I'll probably talk a little bit about how finite state machines work and why they're so important for microcontroller situations. I'll have a number of examples of that. And the reason I want to cover C before I talk about finite state machines is, believe me, I do not want to encode finite state machines in assembly language. You can do it, but I don't want to. And if I don't want to, you don't want to. Right there. You probably don't want to do it in C either, but C it's very easy. The assembly language is very tedious. Loops are the same as C. Again, this is all just review of C. Right there. The flow chart. When you took C, did they make you draw flow charts? Yeah. I never draw a flow chart. For whatever reason, I can't stand it. That there, it's helpful. Now, finite state machines, I do draw. State diagrams. And we'll talk about that. We may even that there. We do have the breaks for loops that there. This is all standard C. Functions work the same. That they're unsigned, long, square, return, X, but it works the same as standard C. And keep in mind that when we call functions, while talking about functions, did anybody talk to you about what's meant by a recursive function? Does the word recursion mean anything? Possibly not. Okay, what recursion is it's a function that calls itself multiple times. Let me give you an example of a recursive function. Right there. Right there. And I may or may not write the code, but what's this doing here? I need one note here. One note here. Okay, let's look at something called a factorial. Does everybody know what 5 factorial is equal to? 5 times 4 times 3 times 2 times 1, right? So, but what is this? Right there. That's 4 factorial, right? What is this? 3 factorial. This is 2 factorial. This is 1 factorial, right? Right there. So I could write a very simple function, call it factorial, and I'm going to call it return long, factorial, right there, and I'm going to pass it x right there. And this function is very, very short, right there. If x not equal to 1, return x times factorial x minus 1. Else, return 1. Right there. It's a very simple C function, right? Because in fact, 5 factorial is 5 times 4 factorial. 4 factorial is 4 times 3 factorial. So all I do is return that there. The problem is I'm calling the same function within the function. That's called a recursive function. That there. And it works perfectly fine for desktop programming. The reason it works fine for desktop programming is that we have lots and lots and lots of memory. We've got 32 gig of RAM, we got 8 gig of RAM, 4 gig of RAM, we got lots of gig of memory. Here we're talking, we've got 2K. If we're operating within the data, internal data, we've got 128 bytes. Well, what happens when we call a function? We push what we're going to pass the function onto the stack, right? The variables we push. We also push the return first we push the return address, right there. And then we push the variables we're going to push onto the stack. And then when we get to the function, it pops off the variables that we want to pass. It does the function, pushes back to what we're going to return onto this. Well, actually, it pops off the program counter, the exact word, right? Doesn't make sense. But we push we push what we want to return back on to the stack is return along with the return address. But we're using the stack to store everything, right? Well, what happens when you use recursion, because we're calling itself back so many times, if we did factorial 120, for example, that means we're going to call this function 121 times. That means we have to have room for 121 addresses. Each address is 2 bytes, right? We've only got 128 bytes. We're going to blow out of our stack. Can't do it. So the only reason I bring this up is this is a huge difference between embedded C and desktop C. Desktop C, there are many, many applications where you're going to use recursive programming functions. you have 8 weeks of C, I think, or 7 weeks of C is what you had. Your C course is broken up half in C and half in the MATLAB. So you did get into recursive functions. But when we look at a recursive function, this is a function that calls itself over and over again. Here's a good example where you would do that. There's the same thing if there's a puzzle where you want to move, say, 4 donuts or sizes from one peg to the other. Well, the way you do that is you move the other ones and then you move the big one and then you move back and forth. And there's a really short recursive function to solve that puzzle. There's lots of places where recursion is very, very helpful to write short, easy code. Unfortunately, it causes a problem with embedded systems. You can't do that because we don't have the stack size. So I'm just pointing out that this is an issue. Since you didn't know what recursion was, you probably wouldn't do it on purpose anyway. But there is something called indirect recursion. Indirect recursion is where function A calls function B, function B calls A back. It's indirect, and it causes the same problem. So when you write embedded code, you have to be very careful when you write functions in C to make sure that the function does its job and returns back to where it's at. It can call another simple function, but you start calling function 5, 6D, it can get, you're going to blow out a stack size. The stack is your enemy. Because it can't be much more than 56 bytes is all you're going to have. It's very, very small, stack size. So as you write in C code, you start calling functions that call themselves or that indirectly call themselves, you're going to end up with all kinds of problems up there. Desktop, I can plug this code in there and just simply let it run, no problem. I can tell what's the factorial of 5,292. It's going to call that function 5,000 plus times. I don't care. I've got stack. I got a gig for stack size. It's no big deal. Here, because I've only got a short amount of stack. So this is just one of those issues that the book doesn't talk about it. No one talks about it. But I've had programmers that got hung up on this because it's not necessarily focused. It's programmers that become embedded programmers. In other words, they're used to writing code for desktop applications. All of a sudden, they're writing code for an embedded system, and guess what? They find that there's things that work on a desktop don't work in an embedded system. So I just wanted to kind of go through and point that out. So the rest of this chapter here is fairly straightforward. Right here, again, where was it? Okay, right here. The rest of this chapter, if we want to initialize the clock, remember before we just use the move command, now we just use the equal command. It's the same thing. This is the name of our special function register. We equal it to 67. That's, at there, use 0x to denote hex, right there. While we wait for the pin to be set. Again, we're using the AND function to see whether or not to zero out all the pins. There, as long as that's not equal to 0, it's going to sit there and spin. Once that pin is set, then it's going to there. Then we go ahead and set our external clock. Our interrupts are fairly straightforward. These are the 5 basic that they're. The only thing that we look at right here, this is how we handle an interrupt service routine in C. It's very straightforward. We just stick at the end of the line interrupt and the interrupt number where it sits on the table. This is a timer 1 interrupt right there. So if we go back to, desktop, what's right here. Again, this is our big nasty view zoom with timers, other peripherals. I'm trying to find where somewhere in here. This is this nasty core up there. See, this shows, this is that 294-page document that everybody loves to read, right? Because it gives you all the nitty, boring details. But buried in this document, and actually right there. Although I'll be honest, when I was writing your final exam, I stole some drawings out of this document, so I did refer to it, but so example right there. What I'm looking for is the interrupt vector table, or the interrupt numbers. You see, if you're laying out a PC board, you need this information for the footprint, right? So that's buried in there. These are all surface mounts. You see, again, we're looking here at our memory space. It goes back to your early question on external right here. This is our program memory. This is our internal data memory, and this is our external memory right here, right there. And this is within the microprocessor right there. But we have to address this as external right there. Right there. There's our special function registers. We're getting closer. Right here. Okay, interrupts. And here we go. And see, these are off by 1 right there. I should point out there's another table. This gives the priority number. You see, this starts at 0, and these numbers are off by 1. That's why I wanted to bring this up here. If you look at the code here, right here, this is timer 1, interrupt service routine. That's interrupt 3. Oh, okay, no, yeah, these are the right numbers. Okay, so that's where this is the table. Actually, that table was later in the chapter. I should have got there, but those numbers do match. It was another processor that they're off by 1. That there, but so in other words, if you wanted a timer 2 overflow, you would just say right here, interrupt 5. So whatever interrupt in this table right here, and I realize that's hard to see, but as you look here, see where this says 3, you go back to this table and you look at what the source of that interrupt is. And that's all you have to do to use interrupts in C. That's the only thing you have to do. Once you put this in here, right there, the compiler will then go through and put in the interrupt vector table the address of the interrupt service routine. And this will, and by putting the word interrupt there, that will change that return when it converts that to assembler to a return on. So writing interrupt service routines in C is very easy. You just tell what interrupt number it is. It's very easy. If we were to look at, and let me pull up an example here. I didn't bring the board, but this is actually Scilabs examples, Blinky, all right. This is Blinky written in C using a timer interrupt, and this is actually going to be our lab for next week. So that they're only that they're. Now these here are just simply put there to make this standalone. This code here actually is in this here. This is really not needed for this code right there. That there. It's just put in there just simply that there. So the code basically is watchdog, disable the watchdog timer. We set up our port right there, and our port there is just simply enables the crossbar and sets port 1.6 as a push-pull. That's all, we're calling that as a subroutine right there. We set up the timer 3 in order to run at 10 hertz right there. And we'll go through this calculation when I go through timers, where we get this number through. And then what happens here is we enable the global interrupts right there, EA equals 1, and we just have this loop that does nothing. See, this is our code that does absolutely nothing. Because the last line of our code is spin forever right there, while 1. We don't even bother putting the semicolon after because it's the last line of code. So all we do is set everything up. But when we come down here, we look at timer 3 right here. Now this particular case right here, timer 3 interrupt 14 right here, right there. And all we do here is we simply clear the timer flag and we flip the LED right there. That's all we're doing. This sets up our timer. This sets up our timer right there with our count value right there. Right there. So every time, and all timer 3 does is we load it up with whatever we pass it counts, and we set it to reload it immediately. When it enable it, we start it. And then when it overflows, it comes back to here, and all we do is clear it and flip the LED off. So we do this is only done once at the beginning, right there. That's only done once to set up our timer. And we'll go through how that's done. Again, it's another boring lecture. That there, setting that there, but it is important because this is better at there, and it's preferable if you're going to have this type of activity that you do use timers at there versus, because when we did the blinky, we did that without using the timers, and we just put in a four next loops essentially. That there. But what this does is it sets up there. But this is our interrupt service routine for timer 3. I could use another timer right there. We go back to this right here. This is using timer 1. Go back to here. Timer and something doesn't jive here. That's timer 3 is 14. Yeah, there's timer 3 overflow 14 right there. So again, as we look at this code right here, we have to know where the 14 comes from. It's really the only thing we need to know to create this. Other than setting the timer, which is a totally separate subject right there. So I think I'm going to kind of stop at this point here. Does everyone get an idea where we're going to see? Because our C code is not going to get much more complicated than this. It will, because we are going to be talking about state machines. And tomorrow I'll introduce state machines that they're able. See if we can get something encoded. The only problem is I have that before to modify it where we put LEDs on it, so we may just have to, when we do the lab, I think next week with the PRX lab, we'll do with a finite state machine where we can actually see LED blinking in a particular pattern that we specify where it goes from one state to the next. So I'm going to go ahead and stop at this point. One, my sinuses are plugging up with sneezing and I can't talk. And I'm already sitting here blowing my nose and sneeze 3 or 4 times. I pity those of you that listen to the lecture. Actually, both my lectures today have been under an hour.